talk. So the one question that I can ask is, if solar energy is cheap, why can't all houses in rural areas, for example, be electrified using solar energy? The problem is they are very expensive. The price has been reduced by more than 100% since 1987, but this is still expensive for guys in the rural areas. The efficiency is still low. We have about 20 to 30 power conversion efficiency. The demand is low. Normally when we talk about low demand, we expect the prices to be low, but the demand is low, and now the companies that are investing in the technology are few, so there is no competition, the price is high. Why do we have low efficiencies? There are different reasons, but in the current solar panels is that the UV photons, most of them are not absorbed. The IR photons are also not absorbed. Only the visible photons are absorbed because silicon absorbs in the visible spectrum. And we also have some reflection at the surface. If we can use like smaller particle sizes, we can actually reduce the light scattering on the surface. And we also have some recombination of charge carriers. We don't want the recombination. We want them to be separated, and then in order for them to be able to in order for us to be able to get charges. I talked about the current solar panels. Silicon absorbs in the visible region, and the sun is rich in the UV and in the infrared. So these photons here are wasted. These photons are also wasted. We need to do something to trap these photons and these other photons here in order to improve the power conversion efficiency. So what we can do, we can create phosphors, which can serve as down converters in the silicon solar cells, or they can also serve as the up converters. The up conversion is absorption of high energy photons and converting them into, converting them into low energy photons, like the UV photons, converting them into the visible photons, or the IR photons and converting them into the visible photons. So you can use phosphors as the down converters or as the up converters. These are examples of phosphors that can be used as up converters. They absorb at 325 nanometers and then transfer to the visible region where cerium where terbium can emit light. So this phosphor here can be used as a down converter. This one can be used as an up converter here. You absorb the IR photons and then you up convert them into the visible photons, and then you can improve the light output of your material. Silicon solar cells, we have made some devices in our laboratories. I will quickly take you through how it works. This is exactly how it functions. You irradiate your material with your solar cells with the sunlight, and then the photoactive layer, you get charge separations here, and then if you connect this, then you can get your light output out of your materials. So what are the challenges with this is that the efficiency is still low. So our challenge is to try and improve the power conversion efficiency of these cells. So there are some concepts for improvement. You can insert a metal oxide layer here, like tin oxide, between the top electrode and the photoactive layer. But now, the first type of metal oxide that was used was titanium oxide. The problem with titanium oxide is that it has got low electron mobility. So currently, this has been replaced by zinc oxide. The advantage of zinc oxide is that it has got a high electron mobility compared to titanium oxide. It also strongly absorbs in the near UV photons, which may cause photo-oxidation and degradation of your material. So zinc oxide can actually reduce the photo-degradation of your material, and it can also improve the lifetime and stability of your solar cell device. I'm going to skip this one. So what we were doing, we're looking at the effects of the particle sizes, the particle shapes, like spheres, flowers, and nanoflakes. Here is just a cross-section here. You can see we have flowers, you have flakes here, and then you have nanoparticles.